So the point of this video is to talk about graphs and how graphs work, graphs that you might encounter in a physics problem. So first and foremost, probably the most common graphs you're going to see are the direct graph and the inverse graph. So the direct proportion follows the form of y equals some constant times x. So if you went in your calculator and you graphed y equals 2x, 3x, 4x, it's going to look like this kind of graph with a line that's steadily increasing with a constant slope. Technically, if something is directly proportional, it also starts at the origin, which is why that line points to the origin of the xy axis. And then in a formula, you can tell a direct proportion if on opposite sides of the equal sign, you have the two variables that are both in the numerator, like kind of shown there. So an example of that. And so looking at v equals f lambda here, we can see that the speed and the wavelength are directly proportional. So there's that. The other kind of proportion is an inverse proportion. So in an inverse proportion, you have on opposite sides of the equal sign, say y is in the numerator, but x is in the denominator. This can also take the form of x times y equals a constant. So if you in your calculator put in, say, y equals 1 over x, 2 over x, 3 over x, they're all going to look like this kind of downward sloping curve. I can tell you that it's not going to look like this. That's a straight line with a negative slope. That is not an inverse proportion. It's going to look like that curve. If you actually plotted this in your calculator, that's the way it would look in the first quadrant, but in the full scheme across the entire, all four quadrants, it would look like that. And we call this curve a hyperbola. And then so inverse proportion is also inverse square. And so inverse square takes the form y equals a constant over x squared. And so the way that would look is like that, but you'll notice that in the first quadrant, both inverse and inverse square take the same shape. So actually, it says, that's why I'm saying inverse proportion, also inverse square. In the first quadrant, they look the same. So as an example of inverse, we have the good old Ohm's law, R equals V over I, and R and I are inversely proportional, which makes sense because as resistance to current flow increases, the current flow is going to decrease because it's a resistance to flow. So yeah, that would be the graph. Wow, that's a really shaky curve. Let's see if I can redraw that. That's a little better. As for inverse square, there's only two equations that follow the inverse square relationship. That's the universal law of gravitation for gravity between two masses, and the electrostatic force for electrostatic force between two charges. And so those relationships, the force is inversely proportional to r squared in both cases. So yeah, inversely proportional to r squared. So if you plotted the force versus r, or r squared, it's going to give you the same shape graph no matter what. So those two graphs, direct and inverse, are going to be your biggest, those are going to show up the most in terms of questions for graphs. I just wanted to point something out in the gm1m2 over r squared and kqq over r squared, in that you have a number of different variables there. So while force might be inversely proportional to r squared, force is directly proportional to mass or to charge. And so for force versus charge, that would be a direct proportion. There is another kind of graph involving a curve, but instead of a downward curve, it's an upward curve, and that's anything that has a square in it. And so direct square is, instead of being direct, you have y being directly proportional to x squared instead of being directly proportional to x. And that graph is going to be in curve kind of going up like that. You might recognize that as a parabola. So if you put y equals some constant times x squared, y equals 1x squared, 2x squared, 3x squared, you are going to get a parabola. And yes, one of my students pointed out, what about the rest of the parabola? Is the rest of the parabola on the other side of the y-axis? Yes, in the second quadrant, it is. but we're only dealing with the first quadrant because we're only dealing with positive values. And a classic example of direct squared would be kinetic energy versus speed. So kinetic energy is 1/2 mv squared. The 1/2 m is the constant, but there's kinetic energy, there's v squared. So you have kinetic energy 1/2 mv squared with the parabola curve. Spring potential energy also follows this relationship. Spring potential energy 1/2 kx squared. And then those show up often, but I can also show you something else in terms of direct and direct squared. Let's take a look at kinematics for a sec. So say Vf is Vi plus At, right? And if we start from rest, we'll say Vi is 0. Then we could just say like the V final, I'll even drop the final. If my V initial is 0, then I don't really need to worry about the final. I'll just say V equals A equal to At. I'm trying to make a point here about the relationship between velocity in time and displacement in time. So with this graph, I can see that V and T are directly proportional. So, I mean, provided that something is actually accelerating, right? That the acceleration is not 0, because if it was constant speed and the acceleration was 0, then you wouldn't have a function. A would be 0, multiply the time times 0, and you have nothing. The velocity doesn't change. There would be V initial and V final would be equal to each other. But let's consider d is VIT plus 1/2 AT squared, and again, if we set VI equal to 0, then the VIT goes away. So I'm just left with d is 1/2 A t squared. And if the acceleration is constant, which we know it is, that piece becomes constant, and it's really the relationship between d and t squared. So we were just talking about the direct square proportion, and this is why the graph slopes upwards when you have a d versus t graph for accelerated motion. But this is a good segue, because the other time you'll see a lot of graphs is when we deal with motion graphs. And so the situations you're going to see with motion graphs, so they're the most common ones anyway, are moving with a constant velocity, so you have no acceleration, or accelerating with a non-constant velocity. So let's start with moving and your velocity is constant. So we basically have three different kinds of graphs that we look at: position, velocity, and acceleration. I usually find it easiest to start with the velocity graph because it's really kind of like it's the motion. The velocity is kind of like what we're looking at first. So this is moving but with a constant velocity. So I want to have a velocity that is not changing. So that velocity is going to be perfectly flat. But if my velocity is constant, my acceleration is 0. So not only will my acceleration not be changing, my acceleration is going to be all the way down at the bottom. A is 0. There is no acceleration. But I am moving, so my position is changing. But how is it changing? The position versus time graph will be steadily increasing at a steady rate. No curve there. Now we have to remember some stuff. So you have position, velocity, acceleration. Let's talk slopes. So acceleration is the slope of velocity. So looking at the situation here with a constant velocity, if my velocity is not changing, then I would have a velocity not changing is perfectly flat. Well, you can see that the slope of that line is 0. And if the slope of velocity is acceleration, then my acceleration value should be 0, and it is. All right, let's take a look at velocity and position, or displacement. So velocity is the slope of the displacement graph. So if I look at the velocity graph, I can see that the velocity has a constant value. And if I look at my d versus t graph, I can see that my slope is constant. So yeah, it's no accident that we have a constant velocity on that blue graph there, and my d versus t graph has a constant slope. All right. Now, the other kind of common situation that you're going to see is that you're moving, but your velocity is not constant. You are accelerating. So maybe my velocity would be increasing. I would have an increasing velocity value. Remembering that acceleration is the slope of velocity. Right? Acceleration is the slope of velocity. I can see that I do have a slope of the velocity graph. The slope is not 0. The slope does have a value, and so the acceleration is not 0. The acceleration is constant, but it is not 0. we can say that the velocity graph has a constant positive slope, and so the acceleration graph has a constant positive value. But what about my position graph? So again, we remember that velocity, oops, that's eraser. Velocity is the slope of displacement. So I notice that my velocity is positive and increasing, and so the slope of my d versus t graph should be positive, that's a highlighter, positive and getting steeper, positive and increasing. And so what do we mean by that the slope is positive and increasing? Well, let's look at what we call the tangent line to the slope. So in the beginning of my curve, like if that's kind of like the tangent line to my curve, it's a positive slope, but it's kind of shallow. But then as time goes on, my slope is getting steeper and steeper, still positive, and getting steeper still. So that is a positive slope that's getting bigger. Just as the velocity, if we look at the velocity graph, right, that velocity is positive and getting bigger. The slope of my d versus t graph is positive and getting bigger. So that's why it curves that way. Also remember that when we're accelerating, displacement is directly proportional to t squared. Oh, where did we hear that before? Oh, wow, look at that. There it is, right? I wasn't making it up. Okay, so all of those graphs go together. And there are other versions of these graphs, like you could have, I saw there was one question that on a Regents, I don't remember which Regents or which question, but it kind of looked like this. And I think it was a multiple choice question, but the gist of the question says, the car is moving in the positive direction, but it's slowing down. What does the d versus t graph look like? So remembering that velocity is the slope of a d versus t graph, it didn't ask for the velocity graph, but let's look at that first. So we have positive velocity, but it's slowing down. And so the velocity starts off as positive, but goes down. First of all, that line right there, that's an indirect relationship, not inverse, indirect. Sometimes people ask me, they're like, will we ever see a graph like that with a downward slope? Yes, in motion graphs, like right here. So like if that shows up, it usually shows up in this type of question. So we have positive velocity getting smaller. Let's see how that would look on the d versus t graph. I changed my color to stay with my own same color scheme. So d versus t graph. Now, it's not going to be, and you say, well, it's the changing velocity graph. The velocity is changing, so it's going to be the one you drew before. No, actually, it won't. And it's like, well, why not? It's like, well, the slope is changing, so the velocity is changing. Yes, but the slope has to change in a particular way, right? So my velocity is positive and getting smaller. So for my d versus t graph, I would need a slope that is positive and getting smaller. So I would have to start with a larger positive value, so kind of like something like that, but then it would need to get smaller, still stay positive, but then get smaller, or shallower, or something like that. And so the curve we are making kind of looks like that. And if I stop making it such a hot mess, I can use my little fancy eraser to do that. Clean it up. You have to be like Bob Ross. You have to make little sounds and stuff when you use your eraser. Oh, no, that was too much. That's not too bad. All right, and so again, to go over why the curve looks that way, we have in the beginning, we have a steep positive slope. In the middle, still positive, but not as steep. And then later on, positive still, but rather shallow, which follows the v versus t graph of being, we have a larger positive velocity, mid-range positive velocity, small positive velocity. If you think this is confusing, I'm not surprised. These kind of graph interpretations in terms of what's happening to the slope can get to be a bit much, but I just wanted to show you that as an example. I can tell you that the two examples that I gave up here, this is what you're going to run into the most often, I would say. All right. One other aspect of motion graphs, we talked about slope, or in calculus, that's the derivative. And then we did not talk about area. or in calculus known as the integral. So let's talk about area for a sec. Okay, so going back to our dVA thing over here, we said that acceleration is the slope of velocity, and velocity is the slope of displacement. Area goes the other way. So displacement is the area under a velocity graph, and the change in velocity is the area under an acceleration graph. And I don't remember ever seeing a change in velocity being from an acceleration graph. I don't think I've ever seen that. But displacement from a velocity graph, you bet. Because it would always just be. So take, for example, this velocity versus time graph that is increasing. And so we know that the velocity is increasing, so it is accelerating. It does have a slope, and so acceleration being the slope of velocity, it does have an acceleration. But we're done talking about slope. I want to focus on the area under the curve. Now, what do I mean by that? So this is what I mean by the area under the curve, between the x-axis or time axis in this case and the actual curve itself. And so if you literally found the area of that shape, if you said that area, which would be the displacement, is 1/2 base times height, that would be equal to the displacement. Now let's take a look at y. Suppose we had some actual numbers here. These are made up numbers, but let's just say on the y-axis we have 30 and on the x-axis we have 20. And I wanted to know how far. Now somebody could just be like, oh yeah, so v equals d over t, and so d is v times t, and 30 times 20 is 600, the end. Wrong. But it's like, wait a minute, v does equal d over t, d is v times t, so why is that wrong? Because let's not forget that v equals d over t is the average value, that is the average velocity. And notice that at the beginning at time zero, the velocity is 0, and at time 20, the velocity is 30. So let's follow the same procedure, but let's try this again. So we have d is equal to, v equals d over t, so d equals v times t, but that's average velocity. And so instead of the average velocity being 30 meters per second, the average velocity would actually be the average between 0 and 30, which is 15 meters per second, times the time of 20 seconds, and how far is actually 300 meters, not 600 meters. Let's see how that compares to my original way of doing it that I advised, which was finding the area, 1/2 base times height. And so if I do 1/2 20 times 30, 20 times 30 is 600, and half of that is, oh, well, you'll look at that. It's the same answer. Right, because I said the area, that displacement is the area under a v versus t graph. So if you just kind of, make that shape underneath the curve and then find the area, even if you have to break it into smaller pieces, like let's just say that the area is not that simple. And it's like, what if I had a funky graph like this with a increasing velocity, and then it steadies out, and an increasing velocity, and it steadies out, and it comes back to 0, and what do? All right, you break the v versus t into pieces. And so I had one funky shape, and then that funky shape becomes a triangle, a rectangle, another rectangle, another triangle, a tall rectangle, and a tall, skinny triangle. So base times height for the rectangle, 1/2 base times height for the triangles. And then for figuring out the numbers for what those bases and heights are, again, using this example, let's make up some numbers. So then I would have, for this first triangle, I need another number here. Let's call this 5. So then 1/2 base times height for the first triangle there, 5 by 5 is 25, and then half of that is 12.5 meters. And then for my rectangle, the base of from 5 to 10 seconds, that would have a base of 5 seconds. 5 by 5 is 25. Then I have another 25 right here. Base is 5, height is 5. And then this triangle up here, the base is 5, but the height goes from 5 to 20. And so the height right there is 15. So 5 by 15 is 75, and half of 75, I think, is 37.5. And then the tall, skinny rectangle, base is 5, height is 20, so that's going to be 100. And then my skinny triangle, height is 20, base is 5, but it's half of that, so that's going to be 50. And if I added all of those numbers up, that's going to give me the total distance. I don't know that you see a lot of graphs like that. This guy, I think like this guy up here is a lot more common, the one that's more basic. But I wanted to show you an example of the area under the curve. So that covers motion graphs. And so again, we have direct and inverse proportion relationships there. We have direct square and inverse square, looking like those curves, but they're examples. This is kind of a motion graph tie-in about velocity versus time having a constant slope, but displacement versus time when accelerating having an increasing slope. And these are the common situations: constant velocity and then not constant velocity, or no acceleration and yes acceleration. The example of getting a d versus t from a v versus t. And then this notion of dVA, where acceleration is the slope of velocity, velocity is the slope of displacement. Going the other way, displacement is the area under a velocity graph, change in velocity is the area under an acceleration graph. Okay, there we go. I hope that was helpful.